On Lesson 8 of Chapter 9, which we're going to compare linear, exponential, and quadratic functions. First, we're going to choose functions using ordered pairs. Then we're going to identify and write functions using data sets. Then we'll solve a real-world problem. So far this year, we've worked with three different types of functions. We have the linear function, which is y equals mx plus b, which forms a line with a downward slope or an upward slope. We have exponential functions, such as an exponential growth function here, or maybe an exponential decay. And that's in the form of y equals a times b to the x power. Then we've had quadratic functions, which are y equals ax squared plus bx plus c, which make a parabola. Today we're going to use ordered pairs and data sets to determine which type of function is which. So for example, it tells us to use the graph to tell whether the ordered pairs represent a linear function, an exponential function, or a quadratic function. So we could plot these points out and we should be able to tell from the points what it is. We have negative 4 and 1 over 32. So if I go to negative 4 and go to try to plot out positive 1 over 32, really close to 0. We have negative 2 and 1/8, so just a little bit higher. 0 and 1/2. 2 and 2. And then 4 and 8, which would be way up here. So if I draw a line connecting these points to the best of my ability, that's the line I get. As you notice over here, we have a very slow increase of amount, but eventually it picks up, it picks up, it picks up. Remember back to a couple chapters ago, that is the characteristic of an exponential growth function. Its rate keeps increasing based on the previous one. So that's what we'll call this, exponential. Now we have this one, which starts out at negative 4 and positive 1, negative 2 and positive 2, 0 and 3, 2 and 4, and 4 and 5. As I make a line with these points, it looks pretty clear to me that I'm drawing a straight line, so that's going to be linear. Now the final one, we have negative 4 and 5, negative 2 and 2, 0 and 1, 2 and 2, and 4 and 5. Plotting these points out, I'm noticing a parabola shape, which it is. We have this axis of symmetry in the middle, the vertex at the bottom, and we have it going down and up. So that's going to be a parabola, making it a quadratic function. We could do the same thing with data sets now. So it says use the differences or ratios to tell whether the table values represent a linear function, an exponential function, or a quadratic function. Extend the table to find the y value for the next x value, then write the function. So as we're looking for the changes between negative 2, negative 1, 0, and 1, that should tell us what kind of function these are. So for example, this is a change of 1 up here. This is a change, it looks like a multiplication is happening, and 0.08 times 5 is 0.4. So we're going to say this is times 5. As we go up 1 again, we see that this is going times 5 again. As we go up 1 again, we're multiplying again times 5. So every single one we go up, we multiply times 5, and that is characteristic of an exponential function. So if we're going to extend this table one more time, we'd say x would be 2, multiply 10 times 5, that would be 50 for our y value. If we're going to write this function then, we know that y equals a times b to the x power. And since we're multiplying times 5 every time, b must be 5. So y equals a times 5 to the x. Remember, we can find the a value when x is 0, because 5 to the 0 power is 1. So when x is 0, y is 2. So we write our equation, y equals 2 times 5 to the x power. So let's erase this as we get ready for our next one. Here I see the x's are all going up 1, so that makes it pretty easy. Now let's look at the changes for this. I see that between this one and this one, y went down 1.5. It went down 0.5, so I know this is not linear. Went up 0.5, and then it went up 1.5. So this is a changing rate, and could it be exponential? Could it be quadratic? A way to check that if it's quadratic is to see if that the rate of change is changing at a similar rate. So if you look at this, I notice that we have negative 1.5, 0.5, positive 0.5, positive 1.5. Every time the rate of change goes up by positive 1. And that tells me it's going to be a quadratic function when the rate of change is changing at the same rate. So I could say quadratic. If we extend this table then, how much is this one going to change? Well, if x is 3, the next rate of change is going to be 2.5. So 2 plus 2.5 is 4.5. And we're going to be working with simple quadratic functions today, meaning that's going to be pretty similar to the parent function y equals ax squared. So to solve for a, we could plug in a value for x and y. Let's do the 1 and 0.5. So 0.5 equals a times 1 squared. 1 squared equals 1. So 0.5 equals a times 1. So a equals 0.5. So as we write our answer here, it would be y equals a, which is 0.5, times whatever x is, squared. Now we could solve a real-world problem. Since the table shows the breathing rates y in liters of air per minute of a cyclist traveling at different speeds x in miles per hour. Tell whether the data can be modeled by a linear function, an exponential function, or a quadratic function, then write an equation for the function. I see that this is going up by 1, which is always very helpful. That helps us get our rates down. Let's see if this is going to be linear. See if it's going up at the same rate. So between 20 miles per hour and 21 miles per hour, or a difference of 1, I have a difference of 5.7 right here. How about this one then? Is this also going to be 5.7? No, this was actually 6.2. So that means it's not going to be linear. I need to check to see if this is exponential. Let's see if it's being multiplied times the same rate. Well, 51.7 divided by 51.4 on my calculator, that's a difference of 1.11 between these two. Let's check this ratio. 63.3 divided by 51.7. Oh, that's also 1.11. So now I know this is going to be an exponential graph. And every time x increases, you multiply it times 1.11 again, meaning that 1.11 is b. If we write our exponential function out, y equals a times b to the x, b is 1.11. So y equals a times 1.11 to the x. Now we need to find a. And to solve that, we could plug in a value for x and y to solve for a. So let's just use 20 and 51.4. So we'd have 51.4 for y equaling a times 1.11 to the 20th power. So to get a all by itself, we can divide by 1.11 to the 20th power on both sides. 51.4 divided by 1.11 to the 20th power, that gives us an answer to the nearest hundredth of 6.38. So that's what a equals, 6.38. So now I can finally write my equation because a is 6.38 and b is 1.11. It would be y equals 6.38 times 1.11 to the x power. That'll be the exponential function for the breathing rates here.